We're going to talk about the second derivatives that relate to parametric functions. And just like the first derivatives, there are more than one second derivative to talk about. We'll start with the simple ones. We have a parametric function, x equals t cubed, and y equals e times 2 to the t. If we're asked to write the acceleration vector in terms of t, well, we know that acceleration is the second derivative of position, or the derivative of velocity. If we want to talk about the acceleration vector, that just means both the acceleration in the x direction, which would be x double prime of t, and the acceleration in the y direction, y double prime of t. Now, because it's x double prime of t and y double prime of t, that means we're taking the derivative in respect to t twice. So we should be able to do that without any real trouble. We can find dx dt is 3x squared. And so the derivative of that in respect to t, or d squared x dt squared, the derivative of dx dt in respect to t, I'm sorry, that shouldn't be 3x squared, that should say 3t squared. The derivative of that would just be 6t. Nothing tricky about that. Similarly, the second derivative in respect of y in respect to t would start by taking dy dt, which is 2e to the 2t. Remember to bring down that coefficient because of the chain rule. And so the second derivative would be 4e to the 2t. And that is my acceleration vector. Very often you'll be asked to find the acceleration vector at a specific moment in time. So write the acceleration vector after 2 seconds. And to do that, you would simply plug a 2 in there and in there. Those are pretty straightforward. The trickier one is the second derivative of y in respect to x. And the reason why that's trickier is because we spoke about this in the last class. When you find dy dx, you do that by finding the derivative of y in respect to t, which we already know is 2e to the 2t, and dividing it by the derivative of x in respect to t, which we know is 3t squared. Okay, nothing different about that. But if I'm going to ask for the derivative of that in respect to in respect to x, so d dx of dy dx, there is a slight complication here. The issue is that what I'm asking for the derivative of, this thing, in respect to x, isn't written in terms of x. So when I find the derivative of this thing, which would be, this is a quotient, so I'm going to use the quotient rule to find the derivative, which, nothing too complicated here. Low d high minus high d low over low low. So the lower one times the derivative of the higher one minus the higher one times the derivative of the lower one all over the lower one squared. Okay, seems pretty straightforward, except I'm taking a derivative in respect to x of an expression in terms of t, which means, maybe you've already guessed where I'm headed with this, this t right here, those are what we call inside functions. So we do have to worry about the chain rule, because of these guys. Well, all that we're going to have to do to fix that is multiply by the derivative of the inside function, dt dx. No problem, right? It's not so hard to multiply by dt dx. Except what is dt dx? The rate of change of time in respect to x. That doesn't make a whole lot of sense. Luckily, there's a little trick here. Instead of multiplying by dt dx, just in general, if you take a number and multiply it by a fraction, so any number times b over c, that is the same thing as taking that number and dividing it by the reciprocal of that fraction. You've seen this before. Dividing by one fraction is like multiplying by its reciprocal. They mean the same thing. So what we can do instead here in our problem is say that the second derivative of y in respect to x is equal to this whole big thing that we had, which I'm going to clean up a little bit as I go here, 12 t to the second times e to the 4 t. I'm realizing and looking at this that I made that t way too big. Also, I'm not sure why that would be a 4. Minus 12 t e to the 2t over 9t to the 4th times, because of the chain rule I had, times dx dt. So again, just to recap what I've just done, instead of multiplying by dt dx, which is the derivative of the inside function, what I'm going to do instead is divide by its reciprocal, dx dt. So I'll put a dx dt in the denominator. The reason why that's convenient is because I do know what dx dt is. So I can write this as 9t to the 4th times 3t squared, because we already know that dx dt is 3t squared. Of course, since those are simple monomials, I will just multiply them together. But I did want you to see where they came from. 9 times 3 is 27, and t to the 4th times t squared is t to the 6th. And if you want to, you can reduce that fraction a little bit, but I'm going to leave it alone so that it's easier to see where it came from. One other little detail that we're going to add here, skip this page, is this idea of something called speed of a particle. When we use parametric functions, we're often talking about the x and y coordinates of something that's moving around as a function of time. And so what we can do is talk about how fast that particle is moving. Now, dx dt and dy dt, those aren't speeds because they're both in one direction at a time, but the particle is moving in more than one direction at a time. And so we have a very, kind of simple formula to remember to find the speed that a particle is moving. It's just that. Hopefully, if you look at that, you kind of see where that's coming from. I'm hoping you look at that and kind of recognize the underpinnings of the Pythagorean theorem in there, because when we talk about a particle and its movement, its dx dt, well, that's its movement in this direction. Its dy dt is its movement in this direction. And so the speed of that particle is how fast it's moving in general. It's almost like how fast it got from here to here. Well, I just drew a right triangle there. So it's kind of using the distance formula or Pythagorean theorem to figure out that speed. And so using this is not that complicated. It's just a matter of remembering that formula. So here's an example. We give you at time t, a particle moving on the xy plane is at position x of t, y of t, where x of t and y of t are not explicitly given. I don't know what they are, but I do know that dx dt is 4t plus 1, and dy dt is sine of t squared. They also tell us some initial conditions, which is not useful for part A. That would be for other parts that come later in this question. So when asked for the speed of the particle at time t equals 3, all that means is to take the square root of dx dt at, or evaluated at, t equals 3, and square that, plus dy dt, evaluated at t equals 3, and square that. That's it. That's the speed. And so we can do that plugging in. Dx dt when t equals 3 would be this when t equals 3, which is 13. Sorry, forgot my square root. And dy dt when t is 3 is the sine of 9. I don't care what that equals. It's obviously something irrational. Whatever that would turn out to be, you can plug into a calculator. This, by the way, would be a calculator question. And we can get a numeric value out of that. And then find the acceleration vector of the particle at time t equals 3. Remember, that's looking for x double prime of t, y double prime of t. Actually, I should say that's asking for x double prime of 3, y double prime of 3. And they gave us dx dt, so we can find the second derivative of that. Remember, these are the easier ones when you don't have to worry about some silly chain rule, because we're taking the derivative of something in respect to t that's actually in terms of t, so that's straightforward. The derivative of that is just 4. And the second derivative of y in respect to t, well, it's a little bit more complicated. It would be the cosine of t squared times the derivative of t squared. And so if we try to plug in a 3 into that, x double prime of 3, sorry, I already wrote that, x double prime of 3 would be just 4. And y double prime of 3 would be the cosine of 9 times 6. So the acceleration vector is 4 and 6 cosine of 9.